Did I miss the papers?
Yeah. Oh, that problem you asked me about, I'm afraid the answer is going to be anticlimactic. Miss a minus sign.
Oh, okay.
And a plus C.
Okay.
That,
That's what I thought.
It must
It must have been something very, very simple.
But,
And I
but you're
couldn't-
right, the second you tried.
Okay, okay. Well, that's good to know. Thank you. Yeah, I see it. I couldn't catch it. I went through like 3 times and then I gave up.
Once you've read it, it's obviously her.
Yeah, yeah, exactly.
You know what it's wrong.
That's why.
Okay, ready for part two. The second part of the lesson tonight is on the Euler-Cauchy equations. And in a nutshell, Euler-Cauchy equations are those that fit into this form. This piece already. X squared y double prime plus ax y prime plus by equals 0. Now, by the way, you probably noticed at this point, all of our special cases that we've looked at in second order have always had a 0 on the right-hand side. The reason is we're building up to the more general situation. It turns out that if you can get two linearly independent solutions to the homogeneous equation, then there is a formula that will give you a particular solution for a non-homogeneous equation. Now, just like with first order linear, it's got some integrations in it. So there's no guarantee that you're going to be able to perform the integrations, but at least you can express the functions in terms of integrals. And by the way, that's not all silliness. Sometimes people feel like, oh, well, we're not getting anywhere if we can only express the function in terms of an integral. Not true. Suppose we knew that e to the t squared, say, was the derivative of the function we want, so that's y prime. Then we know that y is going to be some antiderivative of this, and you could express it this way: it's the integral from 0 to x of e to the t squared dt plus some constant. And then by saying, well, for instance, if you knew its value when x is equal to 0, this thing drops out, then c is its value, right? So you could figure that out. And this part here, you could do with numerical integrator. It won't give you exact solutions, but in a lot of cases, this is a nice enough function, for instance, that as long as x doesn't get too big, this function grows very rapidly. You could get really quite accurate solutions. Or if you had e to the minus t squared, it's just as hard. You can't find a closed form antiderivative. Even for large values of x, you can get excellent values out of this. And I think even our cheap big box store calculators have these capacities now, right? So there is a key in here somewhere. I don't know if I can find it in a hurry. But it is possible to estimate integrals numerically with this calculator. Yeah. Oh, that's square root. Right there. The function integrator, it will estimate, and for nice functions and nice intervals, it does a really good job. So you get many digits that are accurate in a lot of cases. Not always, but in a lot of cases. So, so it is not a huge loss that we're always setting the right-hand side to 0. We're going to get to the place where we'll have non-zero things over there really pretty soon. Okay, now the review that I was going to say last time was this. If you just start with this observation, that if you start with exponential functions, when you take derivatives, you get the function back and some constant multiples along the way. So that suggests that these kind of functions might be solutions to constant coefficient equations. And indeed they are. The general second order linear constant coefficient ordinary differential equation that's homogeneous, you you either get these things or you get something useful from this assumption that you can then convert. And we just walk through those one more time with a mass spring system. So if you look at this equation up here, you're multiplying the second derivative by x squared, multiplying the first derivative by x, and not multiplying by x at all on the original derivative. That would, if you thought about it for a while, you would come up with this observation. I'm sure you all would. You know this, that if you take a power of x, say x to the m, and then you take its first derivative, well, you simply knock the power of x down by 1, right? So if you multiplied, put an x back onto the derivative, then this one and this one would be the same kind of function, an x to the m power. And likewise, if you took a second derivative, you'd have m times m minus 1, x to the m minus 2. And if you multiplied this one by x squared, you would restore that power of x up to x to the m. And then there would be the possibility that these things could add up to be 0, because they would all be some constant times x to the m. So if we start with an equation in this form right here, it is reasonable to investigate the possibility that we will get solutions of the form y equals some constant times x to the m. Now, the constant, of course, doesn't matter, because if you have the constant here, it's going to appear here and here and here, and you just factor the thing back off. So what we're going to do is to assume y has this form, and we're going to plug it into this general form of the Cauchy-Euler equation and see what we get. What's going to happen is we're going to get something like we did before with constant coefficients. We got a characteristic equation. We're going to get another quadratic equation with this one. We've already used up the name a characteristic equation, so for this one, we'll call it the auxiliary equation. Okay, so we know here's our function, the derivatives, we've already written them down. So if we start with x squared y double prime plus axy prime plus by equals 0, then we can plug in these forms that we've developed here. I've got x squared times y double prime, which is m minus 1, x to the m minus 2. And notice this times this, whoops, get back on the screen here. This times this is going to be x to the m plus ax times m times x to the m minus 1. That's this guy right here. Plus b times y, which is x to the m. And we want this to add up to be 0. If we're going to have a solution, that's what we got to have. Well, notice we got x to the m minus 2 times x squared. That's x to the m. X times x to the m minus 1, x to the m, x to the m there. Everything in sight has an x to the m on it. So m minus 1 plus a m plus b, all of that times x to the m equals 0. Now, this right-hand factor here, x to the m, certainly it can be 0. It's 0 when x is 0, right? But otherwise, it's not. So all the action is really taking place over here with this quadratic. So m times m minus 1 plus am plus b equals 0 is a quadratic equation in m that is of interest to us. And you could put it in this form. I tend to work with this one. But if you look in the standard text, you'll see this equation instead. They're both equivalent. You can easily convert from one to the other. Notice if I multiply m times m, I get the m squared here. Then I got minus m plus am is a minus 1 m plus b. And In the same way, you could put, this is m squared minus m, right? So if you minus 1 times m, put that up there, you get this. So they're the same. This is called the auxiliary equation. And as you all can predict by now, there's going to be 3 cases. We could get 2 distinct real solutions. We could get a repeated real root. We could get a complex conjugate pair. And we'll get a different character, a different style of solution in each case. So let's write them down. Case 1, since it's the easiest one by far, m equals m1, m2, distinct reals. Then x to the m1 is going to be a solution, and x to the m2 is going to be a solution, and all possible linear combinations of them, c1x to the m1 plus c2x to the m2 is the general solution. Mathematically, this is not terribly interesting. Now, you might think that none of this is terribly interesting, and I can understand why someone might have that opinion, but what I'm saying is the mathematics here is not deep. We just immediately write down solutions once we land in one of these cases. So case 1, and for an example, suppose we had this one right here, x squared y double prime minus 2x y prime minus 4y equals 0. And I hope that I got one of the right variety. We can solve it no matter what, but I'm hoping this is a case 1 example. Well, the auxiliary equation is this, m times m minus 1 minus 2m minus 4 equals 0. I like to do it this way. In Kraitzig's book, all his examples, he would write it this way. M squared minus, it's minus 2 minus 1, so minus 3m minus 4 equals 0. Well, I'm going to get that very thing on my next step. M squared minus m minus 2m. So whichever way you like it, it doesn't make any difference. Okay, now I'm hoping that this factors and it does. So m equals 4 and m equals minus 1 are both solutions to the auxiliary equation, and therefore y equals c1x to the 4 plus c2x to the minus 1 is the general solution to this Cauchy-Euler equation. And they're just that simple. When you get 2 real roots, you write down this quadratic, solve it, use the solutions for the quadratic as your exponents on x, and you're done. The hardest part about this is remembering, oh yeah, I have this form, and this is the recipe to use. So, you know, I've taught this a number of times, in addition to suffering through it as a student. And to tell you the truth, I can remember just about 0 of the course I took as an undergraduate. So I don't know how well it went for me then. I'm sure I studied these equations because they've been known for a very long time. So I'm sure I did it. I don't remember it. But I have watched other people on their way through it. And people who have trouble with this, generally it's just because they forgot, oh darn, that's a known form, that's Cauchy-Euler. And once they remember and they bring to mind the technique, then, you know, instantly they write down the solution, they get it right. Of course they do. You all have solved quadratic equations now for a really long time, right? Okay, so another possibility is you could get a repeated real root. So maybe if the thing would factor, but it would factor to something like this, the thing. That's not so nice. Maybe the auxiliary, the left-hand side of the auxiliary equation would factor, but you get a repeated factor. So like m minus 4 all squared. Then you got 4 and 4 for your two solutions. So one solution would be x to the 4, but what's the second one? That wouldn't be so obvious. So in this case, if m1 and 2 happen to be equal to the same thing called m, and this is real, not complex, then the general solution looks like this. It's c1 x to the m. That much is predictable. What isn't so predictable is just like last time with the constant coefficient equations, when you had an exponential, I said, well, instead of e to the x, you take x e to the x, and that'll work. Well, it's something like that here. Instead of x to the m, it will be x to the m times the log of x will be the other solution, and I need a constant in there. That is the general solution. And we could prove that, but I think what I'll do instead is I'll do an example, I'll write down the general solution, and then we'll actually check the solution that has the log term and see if it works. So somewhere I should have an example of this. I think it's this one. So we'll solve this one, whether it's the one I want or not. It's a perfectly good example. Okay, so here's my example. X squared y double prime plus 3xy prime plus y equals 0. And I want to write down my auxiliary equation. You know, the reason I like doing it this way, m times m minus 1, is I'm kind of replaying mentally the derivation of these solutions. I know I'm going to take x to the m. I take two derivatives, m minus 1, x to the m minus 2, multiplied by x squared, and I'm back to x to the m. So m minus 1 plus 3m plus, this coefficient is 1, of course, plus 1 equals 0. So that's m squared minus m plus 3m is 2m plus 1. And that, in fact, is m plus 1 squared equals 0. So m is minus 1 and minus 1, repeated real root. Okay, so if I follow the recipe, y equals c1 x to the minus 1 plus c2 x log x, x to the minus 1 log x is the general solution. Or if you prefer to write it this way, c1 over x plus c2 log x over x. So it's probably pretty believable that x to the minus 1 would be a solution, because that's basically, we're almost exactly, you'd write that if you plugged x to the minus 1 in here, except you have minus 1 in all those locations. But this one may be not so obvious. So why don't we grind that out and just check it, make sure that it is in fact a solution. And if it's not, you know, I'll be concerned. And what it would mean is not that Cauchy and Euler got it wrong, but something ran amok in the solutions. All right, so we're claiming y equals x to the minus 1 log x is a solution. And of course, we're trying to prove that. So this is to show that that thing is a solution. Well, derivatives are a little messy, right? First derivative is minus 1 x to the minus 2 log x. And the second term is x to the minus 1 times derivative of log x is, once again, x to the minus 1, which is, sooner or later, we'll want this cleaned up probably, minus log x over x squared plus 1 over x squared. So that's y prime. Y double prime, probably easier to work with this first form here. Next derivative, minus 2 times minus 1, so 2x to the minus 3 log x plus, now taking the derivative on log x, you get 1 over x, so minus 1 x to the minus 3. And then I've got to take the, I left this off here, didn't I? This is x to the minus 2. And its derivative is minus 2 x to the minus 3. Two terms come from that product rule on that, and the x to the minus 2 produces one term in the derivative. Okay, so where was I? I was taking the derivative of this thing right here. It's x to the minus 2 log x, so 2x to the minus 3 log x plus derivative of minus x to the minus 2 is, how on earth did I get here? I have no idea. But this is, I think it's just going to be easier to start clean. Let me rewrite the first derivative in a convenient way. I don't think there was anything wrong here. It was incomplete, but I like this better. All right, second derivative. Minus 2 times minus 1, 2x to the minus 3 log x. Now take the derivative of log x. I'll get minus x to the minus 2 times 1 over x minus x to the minus 3. Now take the derivative of this term. Minus 2x to the minus 3, and now take the derivative of this, 2 times 3 plus 6x to the minus 4. Whew. Okay, so we are going to plug that into the original equation, the ODE, x squared y double prime plus 3xy prime plus y equals 0. And x squared, y double prime is this stuff right here, which doesn't improve too much with simplifying. You can do a little bit for it, but not a lot. Minus x to the minus 3 minus 2x to the minus 3 is minus 3 x to the minus 3 plus 6 x to the minus 4. And that all gets multiplied by x squared plus 3x times the first derivative. That is minus x to the minus 2 log x plus x to the minus 2 minus 2x to the minus 3. And then finally plus y. and y is x to the minus 1 log of x, and we really hope that sums to 0. Okay, this times this, 2x to the minus 1 log x. This times this, minus 3x to the minus 1. And this times this, plus 6x to the minus 2. All right, distributing the 3x on these terms, this times this is minus 3x to the minus 1 log x. This times this is 3x to the minus 1. And this times this is minus 6 x to the minus 2. And finally, the last term, plus x to the minus 1 log x. All right, well, let's see. X to the minus 2x to the minus 1 log x is here. Minus 3x to the minus 1 log x is there. And plus 1 x to the minus 1 log x. Sure enough, 2 plus 1 is 3 minus 3. Those all add out to 0. All right, minus 3 x to the minus 1 is here. Plus 3 x to the minus 1 is here. And those will add up to 0. And what's left is 6x to the minus 2 minus 6x to the minus 2, woohoo, is the 0 function. It worked. So, in spite of the horrendous complexity, the recipe appears to be accurate, at least in this case, it did work. So that's what you do in case 2. So in summary, if you get repeated real root m and m, then y equals c1x to the m plus c2 x to the m log x is the general solution. All right, case 3. All right, we were solving this, m minus 1 plus a m plus b equals 0, which is m plus a minus 1 m squared plus a minus 1 m plus b equals 0. And in general, the solutions are these, negative b, 1 minus a, plus or minus the square root of b squared minus 4 times 1 times c all over 2a. And that, I don't need all that. So we are, if we're in the case of a complex conjugate pair, then it must be that a minus 1 squared minus 4b has to be a negative number. Now, I think I think Krejcik, I forgot to look. I'm pretty sure that he adopts this notation, which if you've studied Greek, you're good to go. But this is mu and this is nu. Oh, unless you learned it in a math class in America, in which case it's mu and nu. Nu, I think you still say nu, right? I forget because I was in college. I took a year of classical Greek, and my professor broke my bad habits of pronouncing Greek like an American. So I don't pronounce it like a Greek person either. I pronounce it like a classical scholar, though I am not. I just took 1 year. Okay.
In the denominator, you have 2a. Is that still 2a, or is it just, okay?
Thank you. It's not going to really matter because in general, when we do this for real, you're going to end up with something like 3 plus or minus 2i, right? So you're going to be looking at the complex conjugate pair. And the question is, what do you do with it? So the two solutions, as before, are this: x to the mu plus I nu, and y2 is x to the mu minus I nu, which honestly doesn't do you that much good. However, you can make some progress with it. It's x to the mu times x to the I nu, and that's y1, and y2 is x to the mu times x to the I nu. Now what we need is to somehow write this in a form where we can get a hold of it. And we can do it. Whoops, I needed a negative right there. So let's work on this one right here, x to the I nu. Now, what I really want to do is write that as an exponential function, e to the something. And probably it's going to be complex. So let's say e to the I theta. Can we do that? Well, if we take the logarithm of both sides, we'd have I nu log x equals I theta. And then, of course, you could throw away the i's. We knew they were going to be there. But theta is equal to nu log x. So that means y1, which is x to the mu times x to the I nu. Well, x to the I nu is e to the I nu log x. And I didn't really need the brackets there, but I do here. X to the mu. But now we know that e to the I theta is cosine theta plus I sine theta, which is nu log x, which hardly fits, but, and I don't have room for my bracket. I'll write that again here in just a moment. Y2 is going to be exactly the same thing, except you've got a negative up here. Well, the cosine is an even function. It doesn't care if you put a negative in there, but the sine is, it's going to have a minus. So x to the mu cosine nu log x plus I, rather minus I sine nu log x. Now, you can do with this exactly what we did with the complex exponentials. Notice, if we were to add y1 and y2, this has got a plus I sine nu log x. This got a minus I sine nu log x. Those would add out, and I'd get twice x to the mu cosine nu log x. So that would be a solution. And really, if I was going to dot the i's and cross the t's, I would have called those z's, because that's usually what we use for complex expressions. But we get this much, which you honestly can tell at a glance. we would expect that x to the mu cosine nu log x would be one of the basis functions of the solution space, and the other one would be x to the mu sine nu log x. So the general solution is this, x to the mu, whoops, I guess I can fix it. I need a constant in here. A cosine nu log x plus b sine nu log x. If you took a times this one and b times this one and added them up, you could factor the x to the mu off and you get that. And if I got good notes, I can instantly pick out an example. Oh, I didn't make one up. Well, let me do a half of an example because I know I can do that in the allotted time. Suppose the solutions to the auxiliary equation are m1 and 2 equals 3 plus or minus 2i. So we can stop saying mu and nu now. We know what they are. Mu is 3, nu is 2. But the solution is going to be this. X cubed, general solution, a cosine nu log x plus b sine nu log x. Okay. Or no. It might make this look more concrete if I could actually generate the differential equation it came from. And in principle, I can. My auxiliary equation has to be equivalent to this. So I'm working backwards here. You don't ever have to do this. I make up all the problems for you and you just solve them, right? But this is how I make up problems. This times this, m squared. Now when I take this product plus this product, I'm going to get minus 3m and minus 3m. That's minus 6m. But minus 2im and plus 2im, the i's go away. Then minus a minus is plus. Then I'll get 3 plus 2, whoops, wrong, 9 plus 4, 13 equals 0. So that should be the auxiliary equation, which could be rewritten this way. Which means that the ODE should be this. X squared y double prime minus 5x y prime plus 13y equals 0. Now, in some languages and cultures, a lot of good poetry is a chiasm. So you have a central thing here, and then this gets reflected here, and this gets reflected here. We'll do a chiasm by solving this thing that we just made up to have the solution that we wanted to have. Okay, so suppose I wanted to solve this differential equation. Then I would say, well, the auxiliary equation is this. And if I simplify it, I get this. And using my quadratic formula, this is the cliffhanger here. 2652 minus 36, 16, So 6 plus or minus square root of 16 is 4. Oh, that was a I, though I forgot that. So I got 3 plus or minus 2I. Those are the two solutions to my auxiliary equation. And therefore, the general solution to my differential equation is x to the 3 times a cosine nu 2 log x plus b sine 2 log x. And if you're so inclined, there is no reason you couldn't take first and second derivatives of this crazy mess, plug it in to this differential equation, and let me just check for a moment. Oh, it adds up to 0. Any question? I have 2 minutes left, and so I'll tell you a story. This one is almost certainly false, but it's good, so I'll tell it anyway. There was the brilliant professor of mathematics who actually could do a lot of solutions simply by thinking of them. So one day in a pause in the lecture, a student said, Professor, on the homework, could you show me how to solve problem number 12? And he thought about it for a moment, and he turned around and wrote on the chalkboard, whatever, x cubed a cosine 2 log x plus b sine 2 log x. And the student, of course, wanted to know how to get there. That's what the answer was, but also wanted to be polite. So she said, could you show us another way of doing that? So he stopped for a moment and he said, I never saw that before, thank you. He turned around and wrote the same thing on the board again. So whatever you think of my lecture style, it's somewhat of it. All right, I wish you all well, and I'll see you on Tuesday. Watch for the assignment to come up on Blackboard, which it surely will, no later than tomorrow.
Have a good weekend.
You too.